Okay, so the next thing that I want to look at is Lewis dot structures. We've all done these before. I know that you use at least semi-dot structures for organic chemistry. You probably use them in other classes as well. So this is just going to be a quick overview. When we are doing a dot structure, we count the valence electrons for each element. And we have to adjust that for the charge. So usually we're looking at a molecule or polyatomic ion of some kind. So let's say I was looking at nitrate. I would be looking at 5 valence electrons for nitrogen, 6 for each oxygen, and then 1 extra one for the charge of a -1. Okay. So this should be even, because the electrons want to pair up. They can be in bonding pairs or bonds, and they can be in lone pairs, which some people prefer to call non-bonding pairs.
So you also have some free radicals.
There are a few molecules that are free radicals, and I will get back to those. For the most part, we're not going to really deal with those because they're not stable enough that we really use them a whole lot in inorganic chemistry, but there are people who definitely study them. So, they're a thing. We're not going to focus on them. Okay. Anybody uncertain how to determine number of valence electrons? Excellent. Okay. So once we have our valence electrons, our most electropositive goes in the middle. So electropositive is the opposite of electronegative. Again, if I think of nitrate, oxygen is right next to fluorine and nitrogen is one further away. So nitrogen is less electronegative than oxygen. So nitrogen goes in the middle. The exception to this is hydrogen, because hydrogen can't form multiple bonds, so it can't be in the middle. Now, what we generally focus on in freshman chemistry is where we have just one central atom. And so we sort of surround that atom with everything else. But as you know from organic chemistry, we can kind of have chains. And so usually if I'm trying to get to a dot structure, instead of just putting the formula in terms of here are all the carbon atoms, here are all the hydrogen atoms, and so forth,
Line drawing.
you'll either have a line drawing or you'll have what's called a condensed structural formula. So if I were going to write, the one I often do is CH3COOH. You may know what that is.
Acetic acid.
Acetic acid, which is found in
Vinegar.
vinegar, exactly. So you could write this C2H4O2, but that wouldn't tell you you're looking at an acid. And so it wouldn't tell you how to place things. And in organic chemistry, we know that it's really important where those oxygens go for how that molecule is going to behave. So if you have a structural formula, you use that to guide the placement of the atoms. For right now, we're going to kind of focus on things with just one central atom to kind of keep our eyes more simple. Not our eyes, our ideas more simple. But if I were going to do the acetic acid, I would join the 2 carbons because the hydrogen can't be in the middle of things. And since this H3 is next to the first one, I put 3 hydrogens around that. And then I have OOH, I would surround the next carbon with those. Since the hydrogen is not next to the carbon, we assume it's attached to the oxygen. So if the hydrogen is attached to the carbon, it will be listed first. And then we have this oxygen up here. And we would use our count of electrons to realize, hey, we need a second bond. Now we can also use the dot structures for the individual elements to kind of tell us what typical bonding is. And by now you are very well aware that carbon likes to form how many bonds? 4 bonds, exactly. If we look at the dot structure for a carbon atom, it has 4 unpaired electrons, okay? If I look at nitrogen, it has a lone pair and 3 unpaired electrons. Well, how many bonds does nitrogen normally like? 3. So unpaired electrons are a good indication of the number of bonds that a particular atom likes to have.
Nitrogen also tends to form like 4 bonds with a plus charge.
Yes, it can do that as well, but that's going to change its formal charge, which we'll get to in just a second. Okay, I want to look at resonance. So let's take a look at ozone. So ozone is O3. So if we think of those oxygens in a line, and oxygen has 6 valence electrons, so we have 18 total to work with. In order to build that molecule with a dot structure, we end up having to have 1 double bond and 1 single bond. Whenever we have a situation where we have external atoms bonded to that central atom that are the same element but have different numbers of, or different bond orders. So I have 2 oxygens on the outside, one of them has a bond order of 2, one of them has a bond order of 1. That's where we see resonance, because it doesn't really matter which of those oxygens has the double bond. So I could draw it the other way, where the atom on the, what is this, my right, has the double bond instead of the one on the left. And both are equally stated. So we would call these equivalent resonance forms. Oops, Q. Or structures. Now, how do I indicate that these 2 drawings here are in resonance with one another? Not the charge, the arrow. Yeah. So we have an arrow that has an arrowhead at both ends. Now, this is different from when we have an arrow pointed one way and underneath it an arrow pointed the other way. That kind of arrow means equilibrium. Okay, that means there's a chemical reaction going on and we're in equilibrium. That is not the same arrow. So on your senior orals, sometimes when you're asked, particularly in biochemistry, if you're asked to do an acid-base problem, and in that acid-base problem, you have a weak acid, there's going to be equilibrium. You got to make sure you pick the right kind of arrows. Okay. All right, so these are equivalent. And that means that they're equally likely to happen, they're equally stable, and we know that we're not actually switching in between these 2 forms. We kind of have something that's a morphed in between stage. So we count the bond order by how many lines we have. So the bond order for a double bond is 2, the bond order for a single bond is 1. But if we're looking at a molecule of ozone, and we measure the bond length and we measure the bond energy, it doesn't look like a double bond. It doesn't look like a single bond. It looks like something in between, okay? We can figure out the bond order, the observed bond order, by finding a weighted average of this. So we take the number of bonding pairs, that's represented by each of these lines, so the number of lines, and we divide by the number of bonds. So remember, when I'm looking at a double bond here, it is a double bond. There's 1 double bond. with 2 bonding pairs. So I take 1, 2, 3 bonding pairs divided by the bond on the left and the bond on the right is 2. And that gives me a 1.5 bond. Now I could also have non-equivalent bond structures. I'm going to draw this out really quickly. Carbon dioxide, you probably can draw that in your sleep, 2 double bonds. Oxygens with 2 pairs of electrons. I had one time somebody draw a structure where I had a single bond on one side and a triple bond on the other side. Is there anything invalid about that structure?
It's just not likely to happen,
It's not likely to happen.
but it
but
could. Under
This
some
has an
circumstances.
octet, this has an octet, this has an octet. So since they all have an octet, they're all equally likely, or they're all valid forms, but they are not equally likely to happen. So I can still draw the arrow in between, but I would call these non-equivalent resonance structures. So before Wednesday, I would like you to read section 1 of chapter 3. And we'll talk about formal charges specifically, and we'll get into what makes the most stable resonance form. For your quiz, I will leave chapter 3 off of the quiz, and so we'll focus on, there's quite a bit of material in chapter 2. So focus on chapter 2 for your quiz. And Ashley, I will have your quiz set up on Canvas. So you can take it on Canvas, but I want you to be on Zoom while you're taking the quiz so that I can prompt. All right?
And
Any
this is
questions?
on Wednesday, right?
On Wednesday, yes.
Okay. Okay, I should be good to take it by then because I'm driving today and tomorrow, but Wednesday's fine.
Okay. Periodic trends is the end of chapter 2. So periodic trends is on the quiz.
Okay.
All righty.